Hariharan, hello.
Hi, ma'am.
How are you?
Fine, ma'am.
You were not there yesterday. I hope you
I
are
have
fine.
exams going on, ma'am.
Oh, so you had test on alkyl halides?
No, ma'am. Computer science.
Computer science. When is chemistry?
Chemistry finished, ma'am.
How was it?
Easy, ma'am.
Okay, that's good. Ashwin, did you get time to go through the previous recording?
No, I have still some more to watch.
Sai Kalyan, what about you? Sai Kalyan, what about you? Hello, are you there? See, that is why I insist that you should switch on the camera, because I don't know whether you are there or not. Hello, Sai Kalyan. Sanjay, did you see the camera that recording that you missed, of the class that
Yes,
you
ma'am.
missed? Okay.
Yes, ma'am.
Hmm. Kalpagesh, Madhavan, did you get time to go through the recording of the classes that you missed? Madhavan?
I'm getting it.
You are? Sai Kalyan, are you there? Sai Kalyan, are you there?
Yes, ma'am.
Yeah, did you go through the recording?
Yes, ma'am. I gone to the recording and took notes, ma'am.
Okay. So if there is any doubt, let me know. Okay, so we'll start our class. 6 of you are already there. Only Hari Raghav is missing. Only Hari Raghav is missing. He will come now. Okay, so we'll start. So yesterday we talked about, when we finished the class, we were talking about vapor pressure. We were talking about vapor pressure. And I told you that if there is a solution, there is a pure solvent or a liquid in a container, then after some, in a closed container, then after some time there will be an equilibrium between the evaporation and condensation, and once that equilibrium is reached, at that point the vapor pressure of the vapors above the liquid is known as the vapor pressure of that liquid at that particular temperature. So what does this vapor pressure depend on was what we were discussing. So the one factor on which the vapor pressure depends, right? One factor on which the vapor pressure depends is the temperature. Okay. So as the temperature increases, you know, the vapor pressure, I showed you with the help of the graph, that as the temperature increases, the vapor pressure of the liquid always increases because the evaporation becomes faster. So more vapor is formed and the vapor pressure of a liquid increases with increase in temperature. The vapor pressure of a liquid is at a particular temperature is characteristic. Okay, so it is a fixed value for a vapor pressure at a particular temperature. For water, this vapor pressure is also, this vapor pressure is also known as sometimes aqueous tension. Okay, so the vapor pressure or aqueous tension of water at different temperatures, it is a fixed value which will be always given to you in case you have to find the vapor pressure of water. Then the other factor on which the vapor pressure depends, I was telling you yesterday, is intermolecular forces of attraction. It is actually, we should say, the nature of the liquid, and under that it depends on the nature of the liquid, and here by that we mean the intermolecular forces of attraction, intermolecular forces of attraction. Okay, so yesterday I told you that these intermolecular forces of attraction, if they are very strong or very high, then the vapor pressure is very low. And if the intermolecular force of attraction is low, then the vapor pressure is very high. Okay, so supposing, and I also told you that compounds like alcohols, they have OH group. So because of that OH group, they show hydrogen bonding. So yesterday we compared the intermolecular force of attraction between water molecules. So this is a water molecule, and between two water molecules, there is hydrogen bonding. This intermolecular force of attraction which exists between two water molecules, it is known as hydrogen bonding, right? And because of very extensive hydrogen bonding, because there can be hydrogen bonding here, there's another hydrogen atom, so there can be a hydrogen bonding here, right? So actually one water molecule can form several hydrogen bonds, one on this side, one on this side, with the oxygen on this side also. So it can form four each between two and several water molecules. You will find lot of hydrogen bonding. So hydrogen bonding in water is extensive, we say extensive. Now when you take ethanol, C2H5OH, here also there is hydrogen bonding between two ethanol molecules. Also there is hydrogen bonding, but the extent of hydrogen bonding is much less compared to water, and that is why the vapor pressure of water is less than the vapor pressure of ethanol. So ethanol will have high vapor pressure compared to water. So which will have higher vapor pressure? Ethanol will have higher vapor pressure. Okay, so when hydrogen bonding is more, vapor pressure is less. When hydrogen bonding is less, the vapor pressure is more. So supposing I take three molecules like this. One is C2H5OH, ethanol. Then another one, you will learn these under alcohols, which is the next chapter that we will do. This is called ethylene glycol. This is known as ethylene glycol. It has two OH groups, right? And there is another one which is called glycerol. It has three OH groups. Okay, propane, 1, 2, 3, triol. It is known as glycerol. You know, glycerol is the boroglycerine, if you have used glycerine anytime. So this is glycerol. So ethanol, glycol, and glycerol. Ethanol has one OH group. This has two OH groups. So this has one OH group, this has two OH group, and this has three OH groups. So tell me which will have higher vapor pressure. Can you tell me which will have higher vapor pressure? Highest vapor pressure, Ashwin, which will have the highest vapor pressure? Anyone?
Glycol, ma'am.
Highest vapor pressure.
Ma'am,
Let me change my question. Which of the three will have highest intermolecular force of attraction? Which will have maximum hydrogen bonding? Can you tell me? Which will have maximum hydrogen bonding? Sai Kalyan, which will have maximum hydrogen bonding?
Glycerol, ma'am.
Glycerol will have maximum hydrogen bonding, right? Because it has three OH groups. So hydrogen bonding will be maximum in glycerol, and then in glycol, and the least will be in ethanol, right? Now, if it has maximum hydrogen bonding, what does it mean? It has highest intermolecular force of attraction. So which has highest intermolecular force of attraction? Glycerol has the highest intermolecular force of attraction. So if I take IMF means what? Intermolecular force of attraction. So IMF, if I compare, then ethanol has, so if I write here C2H5, I should write here ethanol. So if I write here ethanol and ethylene glycol and glycerol, maximum intermolecular force of attraction is of glycerol. Okay, so glycerol has the highest intermolecular force of attraction. So what will happen to the vapor pressure then? Which will have the highest vapor pressure? Highest value of vapor pressure will be where? Which will have the maximum vapor pressure? Ethanol, glycol, or glycerol? Vaishnavi?
Ma'am, ethanol will have highest vapor pressure.
Ethanol will have highest. So if I compare vapor pressure, then ethanol will have highest vapor pressure, and then glycol, and then glycerol. I hope you all understand now what I'm trying to say. And as I showed you in the graph yesterday, as you keep on increasing the vapor pressure, when the vapor pressure becomes equal to the atmospheric pressure, that is the temperature when the liquid starts boiling, right? So here you'd said ethanol has the highest vapor pressure, right? Now I want to compare the boiling points. Okay. Now which will have the highest boiling point? Now again I will write ethanol, glycol, and glycerol. Okay. So ethanol has the highest vapor pressure and glycerol has the lowest vapor pressure, right? So which will have the highest boiling point? Hari Raghav, can you tell me which will have the highest? Huh?
Ma'am, is it ethanol?
No, what is the, supposing I give you some arbitrary values. Ethanol has a vapor pressure which is equal to, say, 78, 0.78 atmospheres, right? And this has a higher, this has the highest. Now this has a vapor pressure, say 5.56 atmospheres. And this has a vapor pressure 0. Okay. And this has a vapor pressure of 0.36 atmosphere. For it to boil, reach the boiling point, it should, the vapor pressure should reach what pressure? It should become 1 atmospheric pressure. So which will reach 1 atmospheric pressure more quickly?
Glycerol.
No. Highest.
That's low atomic pressure.
Yeah, whichever has highest vapor pressure, in highest boiling point will be the one which has the lowest vapor pressure. So glycerol will have the highest boiling point, and then glycol, and then ethanol, right? Because this is 0.78, it will very quickly become 1 atmosphere. So when you start increasing the temperature, it will very quickly reach 1 atmosphere. So its boiling point will be the least. And glycerol has a low vapor pressure. So to reach 1 atmosphere, you will have to heat it for much longer. So its boiling point will be much higher. Did you understand now the relation between vapor pressure, intermolecular force of attraction, vapor pressure, and boiling point? Did all of you understand that properly? Yes? Sanjay? Yeah.
Yes, ma'am.
Okay. So now what we have to do, so these are, this is when I talk about vapor pressure, then we are talking of the vapor pressure of a pure substance, pure liquid, vapor pressure. Now, we will talk about 2 types of, yeah, tell me.
These 3 things will differ in their structures.
Yeah, these three have different structures. One has This has one OH group, this has two OH groups, and the third one has three. So it can have hydrogen bonding at 3 points. So it will have a stronger intermolecular force of attraction. When there are two, it will have lesser intermolecular force. And ethyl alcohol, it has only 1 point of intermolecular force of attraction. So since the intermolecular force of attraction is less compared to glycerol, it will change into vapor very easily. And when it changes into vapor, its vapor pressure will be high. So the vapor pressure of ethanol will be highest and vapor pressure of glycerol will be the lowest. And since the vapor pressure of glycerol is the lowest, its boiling point will be the highest. Do you understand now?
Yes.
Okay. Now we have to talk about the vapor. So this was a pure solvent. We are talking of vapor pressure of liquids, and this is a pure liquid, the vapor pressure of pure liquid. Okay. Now, if there is, if we have to make, now we have to talk about vapor pressure of solutions. Okay. So vapor pressure of solutions. Okay. Now there can be, when we talk of solutions, first you should understand we are going to talk of those solutions where we are mixing two liquids. Because if I take a solution of a solid and a liquid, where the solute is, if the solute is solid and the solvent is liquid, right? Then what will be the vapor pressure of the solution? We will talk about it later. But for solids, you should know that the vapor pressure of solid is always 0. So if I take the pure solid, so pure solid, if I call it P0, that P0 is equal to 0. For solids, the vapor pressure is 0. You understand that, right? Because solids don't evaporate on their own, right? So if I keep a solid block of sodium chloride, or if I take a solid block of copper or zinc and keep it there, it doesn't evaporate, right? It cannot evaporate at room temperature or lower temperature. Even the melting points is in thousands. Okay. So solutes which are solid, their vapor pressure is equal to 0. Now, supposing we take a liquid. Now, if we take two liquids, so now we take solutions of two liquids. Solutions of liquid plus liquid. So where our solute is also a liquid and our solvent is also a liquid, and both of them have a vapor pressure. Okay. So let us take one liquid here, right? A liquid which is, say, A, right? This is in a closed container and this is a liquid A. Now the vapor pressure, let us assume that the vapor pressure of the pure, so this causes some vapor pressure, and the vapor pressure of pure A, we will call it P0A. P0A is a vapor pressure of pure A. Now similarly, in another container, I take another liquid which is, say, B. This also exerts some vapor pressure, right? Now this vapor pressure is of pure B is P0B, right? Now when I mix A and B. Okay, so in the third container, I have mixed A and B. So I have A and B. So what will be the vapor pressure now is the question. What will be the vapor pressure now? Will the vapor pressure now be equal to P0A plus P0B? P total, will it be equal to P0A and plus P0B? Can we say that? We cannot, because when we mix the two solutions, first of all, there can be interaction between vapors. There can be so many things which happens. Most importantly, the amount of vapor each liquid forms depends also on the mole fraction, on the amount of A and the amount of B. If you mix equal amounts of A and B, then probably we can say it is P0A plus P0B, 50% vapor pressure of A and 50% is of B. But if our A is 80% and B is only 20%, then 80% of the vapor will be because of A and 20% of the vapor will be because of B. So here one scientist named Raoults, R-A-O-U-L-T-S. So he gave a law which is called Raoult's law. So what does the Raoult's law say? The Raoult's law states that the vapor pressure of a liquid in solution is proportional to its mole fraction. Okay, so mole fraction means the amount of vapor. You know what mole fraction is: the vapor pressure of A divided by the the moles of A divided by total number of moles. So what did he say? That here the total pressure of A, which we call PA, and total the pressure of A in solution is PA and pressure of B in solution is PB, and PA is proportional to the mole fraction of A and PB is proportional to the mole fraction of. Okay, so what did Raoults say? That the vapor pressure of a component in a solution is proportional to its mole fraction. Okay, is proportional to its mole fraction. Now let us go a little further. So if I say PA is proportional to
Ma'am.
XA, yes,
Ma'am, can you for a second go to the before slide now?
yeah.
Yes, ma'am. Yes, thank you.
So PA is proportional to XA. So if I want to remove the sign of proportionality, I can say PA is equal to a constant into K into XA. The constant here is the vapor pressure of pure liquid, because vapor pressure of a pure liquid at a particular temperature is a constant. So K here is equal to P0A. So if I substitute the value, PA is equal to what? PA is equal to P0A into XA. P0A into XA. Okay, what is XA? Mole fraction of A. What is mole fraction of A? Number of moles of A divided by total number of moles. Similarly, PB will be equal to what? It will be equal to P0B into P0B into XB. All right. So total pressure of the solution, we can call it PT, is equal to PA plus PB. Okay, is equal to PA plus PB. Now this PA is called the partial pressure. Yes, tell me.
Here PA is the partial pressure and P naught A is the vapor pressure, ma'am.
P naught A is the vapor pressure of the pure liquid. P naught A is the vapor pressure of the pure A. And PA is a partial pressure of A. Okay.
Okay, ma'am.
So this is PA here is the partial pressure of A. Right? And P naught A is equal to is the vapor pressure of pure A. All right. So total pressure is the sum of, because you have learned last year Dalton's law. Similarly, here also the total pressure is equal to the sum of partial pressure. So what is,
Ma'am, but you told Raoult's law is vapor pressure proportional to the mole fraction. Here you're written
yeah,
partial.
yeah. So yes, there is a little, I should say clearly, Raoult's law states that the partial pressure of a component in a liquid is proportional to its mole fraction. Partial pressure is proportional to mole fraction, and the total pressure is equal to the sum of partial pressure. Okay. So partial vapor pressure of a liquid in a solution is directly proportional to its mole fraction. Okay, so what does the Raoult's law say? Raoult's law also, let me write here. Raoult's law, it states that the partial vapor pressure of a liquid is in solution is equal to, no, not equal, it is proportional to the mole fraction, proportional to its mole fraction, proportional to its mole fraction in the solution. Sai Kalyan, thank you for pointing out. I didn't emphasize that here. Raoult's law says that PA is, so PA is the partial pressure. PA is proportional to the mole fraction of A, and PB is proportional to the mole fraction of B, right? So from here I got this. Okay, so now can we, so we can substitute it further, and we can say PT, we'll write from here.
Can you go up second go to the yes.
What is it?
1 minute, ma'am. I'll copy this. Copy just the. Yes, ma'am.
So PT is equal to PA plus PB. And if I substitute, then I can say PT is equal to P0A into XA plus P0B into XB. Okay. Let me write X in a way so that both are different, into and XB. Okay. So based on this, let us do one question. Okay, now please, all of you, if you have understood what I have taught, please do this question. So vapor pressure of ethanol and methanol are, now when I say vapor pressure of ethanol and methanol, I mean P0, P0 of ethanol and P0 of methanol. Calculate the vapor pressure of the solution containing 60 grams of and 60 grams of ethanol and 40 grams of methanol. Also find the mole fraction of methanol. Okay, so how will you do it? Take some time and do it. So what do we need to do first? Tell me. Ashwin, what is the first thing that we should do? Ashwin? We need to find the total pressure, vapor pressure of the solution using this formula, right? Now, in this formula, what are the things we have? We know P0A. P0A is what? P0. Instead of P0A, I will write P0 ethanol. So instead of writing ethanol, I will write P0E. P0E. That is equal to ethanol and methanol. So this is 44.5 millimeter of mercury. And P0M is equal to 88.7 millimeters of mercury. All right. Now we need to know the mole fraction of A, right? How will we find the mole fraction of A? A is, say, ethanol. So to find the mole fraction of A, so XA will be equal to number of moles of E divided by number of moles of E plus number of moles of M. Can I find the number of moles now? Tell me. Ne will be equal to how much? Who will tell me? Ashwin, can you tell me how will I find the number of moles of E? Kalpakesh, Madhavan, tell me, how will I find the number of moles of E? Madhavan,
Yes, ma'am. This one.
how will I find the number of moles of ethanol? Can I find? It will be equal to mass of ethanol divided by the molar mass, right? You know that? So what is the mass of ethanol, Madhavan? Look at the question and tell me the mass of ethanol. What is the mass of ethanol?
140.
Madhavan? 40.
40.
Ethanol. We are doing ethanol, no? So mass is 60.
Yeah.
Right. And what is the molar mass of ethanol? Can you find out molar mass of ethanol? You know the formula of ethanol. Ethanol is what? C2H5OH. Who will find the molar mass quickly? Tell me.
Ma'am, is the answer 2 moles?
46.
46. It is 46, right? So C2 is 24 and H6 is 6 and oxygen is 16. So you add up, it will become 46, right? So 60 divided by 46 is how much? It is equal to 1.304 moles. Now similarly, find NM, methanol. Who will tell me? Sanjay, can you tell me what is the mass of methanol? Tell me, Sanjay.
So
In the
40 by
40 divided by molar mass of methanol. Has anybody calculated molar mass of methanol?
Ma'am,
32, ma'am.
32.
32. Very good. 32. So this is 32. So 40 divided by 32, you will get 1.25. This is moles. Right? We anyway have to find the mole fraction of methanol. So what is the mole fraction? Let us find mole fraction of both. So first find the mole fraction of ethanol, right? Ethanol. Hariharan, can you
Ma'am.
tell me what will be the mole fraction of ethanol? It will be Ne upon Ne plus Nm, right? Now can you tell me? Hariharan, are you there?
Ma'am.
Yeah, tell me. What is NE?
42, ma'am.
We just calculated here. What is NE?
Sorry, 46, ma'am. 46, ma'am.
No, that is that is a molar mass. What is number
Molar
of mole? We have to find the number of moles, right? What is the
Oh,
number of
yes.
moles? Yeah. So it is 1.304 divided by 1.304 plus 1.25. Are you all getting what I am teaching? Sai
Yes, ma'am.
Kalyan, can you find out the answer quickly? You have a calculator anyway?
Ma'am, is for ethanol is it 1.1 ma'am mole fraction?
1.25.
No,
40.
I'm saying the mole fraction, ma'am.
Okay, mole fraction of methanol. Okay, mole fraction of methanol will be 1.25 divided. This is for methanol. Mole fraction of methanol is 1.25 divided by 1.304 plus 1.25. So what are the two answers? Who found out? Tell me.
For me, ethanol something like 0.510 is coming, ma'am.
Right. So this is 0.51. And this one will come to 0.49. All right. Do we write any unit for mole fraction? No, mole fraction is a fraction. It has no unit. And you should always see that the sum of the mole fraction of two components should be equal to what? It is always equal to 1. So the second one you could have just subtracted from 1 and you would have got 0.49. You can see 0.51 plus 0.49 is equal to 1. So sum of mole fractions is always equal to 1. Okay, so we got the mole fraction of both of them. Now can we calculate P total? So P total is equal to vapor pressure of will be P0A into XA plus P0. Now instead of A, I should make it E, right? Because of ethanol and methanol, let us change it. So this is P0E plus XE, and this is P0M plus into XM. Okay, now somebody quickly find out. Right, so P0E is
Ma'am,
given.
can we get in the same units the values of the vapor pressure?
Yes, it is given here. Ethanol is 44.5 and methanol is 88.7. So P0E for ethanol is 44.5 into 0.51 plus 88.7 into 0.49. Did you all understand?
Yes.
So this comes to 22.69 millimeter, and this comes to 43.46 millimeters of mercury. And if I add the two, I will get 66.15. 66.15 millimeters. So this is how you can do simple questions on vapor pressure. So if there are two liquids which are mixed together, you can find out the vapor pressure of the solution by finding the partial pressure of each component with the help of the mole fraction and the vapor pressure of the pure component. And add the two, that means add the partial pressure of all the components, you will get the vapor pressure, total vapor pressure of the vapor in a mixture of or in a solution, total vapor pressure of a solution you can find. Okay, so this is one question. Now I want, so that you all are thorough in this, I want you to do one more question. Now this time the question is, there are two, in a solution, there are two components. One component is cyclohexane. Okay, cyclohexane, and the other component is ethanol. Cyclohexane and ethanol, and their vapor pressures are 280 millimeter. When I say write millimeters, please understand it is of mercury only, right? And for ethanol, it is 168 millimeter of mercury. Now, mole fraction XC, mole fraction of cyclohexane is already given. It is 0.32. And P total is given as 376 millimeter. Now, before I tell you the question, I must tell you in the previous question, whatever value 66.15 millimeters of mercury that I got it because I assumed that my solution is an ideal solution. Okay. So what is an ideal solution? Ideal solutions are those solutions which follow the Raoult's law, right? Ideal solutions are those solutions where the total vapor pressure is equal to the sum of the partial pressures of each component. Okay. Now let us see whether this solution is an ideal solution. We have to find whether the given solution is ideal solution. The P total of this solution found experimentally is 376 millimeters of mercury. Now you find out based on the data that is given to you, the vapor pressure of the mixture. How will you find the vapor pressure of the mixture? Vapor pressure of the mixture P total according to us should be P0C into XC plus P0E into XE. Okay, what is P0C? Tell me. The vapor pressure of pure cyclohexane, which is given as 280. Right? And what is the mole fraction of C? XC is given. So into 0.32 plus P0E, that is vapor pressure of ethanol, that is 168 millimeters, into mole fraction of XE. What is mole fraction of XE? Can you tell me? Anyone? Who will tell me the mole fraction of XE? I know the mole fraction of C. So what is the mole fraction of E now? Tell me. Who will tell me? How will you find out?
Ma'am, 1.70 something.
Why? How did you find that? We don't know how much of ethanol and how much of methanol is there. I only know the mole fraction. I told you just now, XC plus XE. Sum of mole fractions is always equal to 1.
Ma'am, here P total is given as 376 now, ma'am. So
we don't have to, no. We can't find out from P total because this is an experimental value. We want to find the theoretical value. Then compare and find out whether the given solution is an ideal solution. This part you leave. Now we have to find XE. XE we can find because the sum of the two mole fraction. So it will be 0.68. So this into 0.68. All right. So if we put in the values, What will we get? Use your calculators, children, right now. So if I do that 280 point, let me do 280 into 0.32, how much is it? Somebody find out. Nobody is there. I only have to do the.
It is not ideal solution, ma'am, because
So what is the total that you got? What is the total that you got?
the coordinate is coming as 203.84.
Very good. 203.84. This
This is
whole
a-
thing, if I do the calculation, what is the vapor pressure that I am getting? 203.84, right? If the total pressure, which I should have been 203.84, but what is the total pressure? It is 376. So this is a non-ideal solution. Okay, did you understand? When I mix the two solutions, the vapor pressure should have been 203.84 millimeter of mercury, right? But actually the vapor pressure has become higher than that. It is showing a positive deviation, right? What is the vapor pressure? It has become more than expected. Now, how can the vapor pressure become more than expected? Now, sometimes when you mix the two volatile liquids, then the vapor pressure of the mixture should be what is expected. Then it is ideal solution. But if it is more or less than expected, then it is a non-ideal solution. Now, the question is, how does the vapor pressure of a liquid, of a solution become more than expected, or why does it become sometimes less than expected? So we have to understand the non-ideal solution. So now next thing that we have to learn is the non-ideal solutions. Okay, so let me take an example of one solution where you have say this compound. What is this compound? Can you tell me? Can anybody recognize this compound?
Ethanol. Ethanol.
No. If I write it like this, probably you will understand. What is this compound?
CH.
Ma'am, prop 2.
Prop-2-one or propanone, or commonly known as acetone. Propanone or acetone. Okay. What you learn, children, in 11th standard, you can't forget. I know chemistry is a volatile subject. It must have evaporated, but please keep revising. So this is acetone. Now, there is another solution, another liquid, which is this one. Right? This is, if I write it together, it is CHCl3. Now, when I taught you alkyl halides, I told you the name of this compound. This is chloroform. Okay. So there are two liquids I have taken. One is acetone and one is chloroform. Now, I don't know their vapor pressures. I don't know, but I'm trying to predict what will happen. Will they behave as ideal solutions if I mix acetone and chloroform? Now, when I take, it all depends on intermolecular force of attraction. You should understand that. Now here, what sort of intermolecular force of attraction is present in case of two molecules of acetone? Now, acetone has carbon-oxygen bond, which is a polar bond, right? So oxygen is delta negative and carbon is delta positive. Now I take another acetone molecule here. So this is one acetone molecule, and this is another acetone molecule. C double bond O, and here CH3 and CH3. This is delta negative and this is delta positive. So between this delta, this is polar molecule, and this is also a polar molecule. Now polar molecules act like dipoles. Dipoles means small magnet sort of things, okay, dipoles. So between this delta positive and negative, there will be a force of attraction. Okay, so between acetone molecules, what is the type of force of attraction? We call it dipole-dipole interaction. Dipole-dipole interaction. Okay, so there is some dipole-dipole interaction between the molecules of acetone. So two acetone molecules attract each other by dipole-dipole interaction because there is a polar bond. Now you look at chloroform. Chloroform also, you see there is carbon which is delta positive and chlorine which is delta negative. So here also, what type of intermolecular force of attraction is there? It is dipole-dipole interaction. Okay, some different type between, but still this is also dipole-dipole interaction. So I had two liquids. One is acetone, where the atoms or molecules of acetone are attracting each other by dipole-dipole interaction. And I have chloroform, where the molecules of chloroform are attracting each other by dipole-dipole interaction. Okay. So if I say acetone, so it has A, one molecule of acetone is A, and it is attracting another molecule of A, acetone, by dipole-dipole interaction. This is dipole. Similarly, for chloroform, let us see, it is B and B also are attracting each other by dipole-dipole interaction. Now I mix the two solutions. When I mix this two solutions, what happens? This is acetone, C double bond O. And this is chloroform, HC chloroform, CHCl. Now there was some interaction between A and A, there was some interaction between B and B. Now we have mixed them together. So now a new interaction is there between A and B. And this interaction between A and B is stronger than the interaction between AA and BB. Okay, because why? Because now it has become like a hydrogen bond. Okay, so when hydrogen is closely attached, this interaction is greater than the interaction between AA and BB. So if I write here A and B, there is a stronger intermolecular force of attraction. This is stronger, right? This interaction between A and B, it is stronger than AA and BB. Then what will happen? Can you guess? Okay. So now a new interaction is there between A and B, and that interaction is stronger than AA and BB. So what will happen to the vapor pressure? The vapor pressure of the solution will become less. The vapor pressure, if the interaction of AA and BB were same as interaction of A and B, then the vapor pressure, then it would have been ideal solution. But now the vapor pressure has reduced. Why the vapor pressure has reduced? Because the intermolecular force of attraction has increased. And so there is a deviation in the intermolecular force of attraction. Deviation in the, deviation in the vapor pressure. The expected vapor pressure the vapor pressure which you find will be less than the expected vapor pressure. So that is a deviation in the negative direction. The calculation that we did was a deviation in the positive direction. Okay. Now to understand this negative and positive, so let us write down here. So there are two types of non-ideal solutions. Okay, so let me compare the two non-ideal solutions. Okay, so I'll compare the non-ideal solutions. Solutions, these are both non-ideal. So solutions which show positive deviation and solutions which show negative deviation. Solutions which show positive and solutions which show negative deviation. So the first thing is, in solutions which show positive deviation, what will happen? Solutions which show positive deviation, then their AA interactions, AA and BB interaction, AA and BB interactions are more than AB interaction. Okay, so when you mix the two, then there is no interaction between A and B, so the vapor pressure tends to increase. So here P total is more than P0A plus P0B. Okay, here what happens? AA interaction, AA and BB interactions are less than AB interactions. So that means AB interactions are more. If AA interactions and BB interactions are equal to AB interaction, then it will be ideal solution. Now here P total will be less than P0A plus P0B. Okay, so that means there is a negative deviation. And here there is a positive deviation. Here the vapor pressure of the solution will be more than expected. And here the vapor pressure of the solution will be less than expected. Okay, now the two other factors which are important here, which you should know, is that when I mix the two solutions, when it is positive deviation, that means the vapor pressure of the solution is more than when I mix them. So change in volume, delta V. Here the volume is also increases because less interaction. So is delta V is the volume increases. Instead of this, let me write here the volume, the total volume increases. The volume of mixing increases. The volume increases here, and here the volume decreases. Right? And the third thing that you should know is the boiling point. Now, what will be the boiling point of a solution which shows positive deviation? So boiling point of the mixture should be in between the boiling point of the two. So if the vapor pressure increases by mixing the two, what will happen to the boiling point? The boiling point of the mixture will be less than expected. And here boiling point will be more than expected. Will be more than expected. Now, most importantly, the examples. Okay, what are the examples of solutions which show positive deviation and the examples of solutions which show negative deviation? So I will give you a list. So for positive deviation, it is, one of So solutions which show positive deviation, they are water plus methanol, H2O plus ethanol. One of them, if both have OH bonding and they have different extent of hydrogen bonding, then it generally shows positive deviation. So this had some hydrogen bonding, this had some hydrogen bonding. And when you mix them together, the hydrogen bonding of water weakens and so the vapor pressure increases. So this is, now you can write, if one of them is an alcohol, it is generally positive deviation. Then you can have acetone and ethanol. Acetone plus ethanol. Okay. And for negative deviation, you have one of them is generally an acid. So you can have HCl plus water. You can have HNO3 plus water. Any acid, HNO3, not HCl, HNO3 plus water. These will show all positive, negative deviations. Then I already gave you one, chloroform plus acetone. Then you could also have acetone plus, chloroform plus benzene, CHCl3 plus benzene. Okay, so these are all examples of non-ideal solutions. I should also give you examples of ideal solutions. Ideal solutions are generally those solutions which are similar in nature. Then they will be ideal because then their intermolecular force of attractions will be similar. So if I want to take ideal solutions, so in case of ideal solutions, the examples are like you could have benzene plus toluene, benzene plus toluene, then ethyl bromide, ethyl chloride plus ethyl bromide. These are all ideal solutions. Okay, there you can make out they are similar compounds. Okay, and then you can have N-hexane plus N-heptane. Okay, Then you can have chlorobenzene plus bromobenzene. Okay, so these are examples of ideal solutions. In case of ideal solutions, you know P total is equal to P0, PA plus PB. I made a mistake here, children. Please correct it. Not P partial, then I should put partial pressure also. P here. Please make a correction, not the partial pressure, it is the vapor pressure. Not the vapor pressure, but the partial pressure, sorry. So partial pressure. The P total is not, is more than the partial pressures of both. Okay. And here AA interaction is equal to BB interaction. AA interaction and BB interaction is similar to AB interaction. Same, both are similar. So there is no change in the vapor pressure. So expected vapor pressure and the vapor pressure, if they are same, then it is ideal solution. Now, sometimes there is also a graph which is asked here. So which you should be able to understand. So this is a graph for which we generally use for showing the vapor pressures of two liquids, solutions of two volatile liquids. So two volatile liquids. So how do you draw a graph and how do you interpret it? So this here on this y-axis, I have taken vapor pressure, and on x-axis it is mole fraction. Can you see the graph? So XA here, mole fraction of this is two solutions A and B. So here XA, that means mole fraction of A is 1. What does it mean? It is only 1. The component B is 0. So mole fraction of B is 0 and mole fraction of A is 1. So at this point here, it is only A. And what is the vapor pressure of A here? That is vapor pressure of pure A. That is P0A. Okay, vapor pressure of pure A. Now, when I mix it slowly together, as the mole fraction changes, right, the P total changes. And here P2, this, so here PA as the, this is PA. Here, as I am adding the other component B into it, what is happening to the vapor pressure, pure vapor pressure of pure A? It will slowly increase or decrease because PA is equal to mole fraction. So as the mole fraction of A is decreasing, what will happen? The graph is going down. You can see the line is going down. Line. Right? It is going downwards. Why? Because the mole fraction is slowly decreasing. On this side, this is the vapor pressure. P0B is the vapor pressure, pure vapor pressure of the pure component B. And as the mole fraction of B is decreasing, you can see the line graph is going down here. Here, XB is 0 and here XB is 1. Okay, mole fraction as it is decreasing, the graph. So this line here shows the partial pressure of XA, and this shows the partial pressure of XB, right? And if I join the two lines, that will give me the total pressure of the two components, which is the partial pressure of A plus the partial pressure of B. All right. Now, if I have a solution which is showing negative deviation, Okay, a solution which is showing negative deviation. Then how will the graph look like? Let me take another color, green. Okay, so negative deviation means the total pressure will be, this is the expected pressure. The total pressure now will be less than the expected pressure. This is showing the negative deviation. Okay, so here as I change the mole fraction, this pressure will be also less than expected, and this also as a fraction changes, right? So this graph shows, what is this graph showing? This graph is showing negative deviation. You can understand negative deviation now easily, because if I find the pressure, if I want to find the vapor pressure of the two mixtures here, it will be here and not here. So that means there is a negative deviation. Now the same graph, if I copy, now you see this graph. And in this case, now I want to show you a positive deviation. So if I want to show a positive deviation, then what will happen? Positive deviation means that the total pressure is more than the sum of partial pressure. So where will be the graph now? It will be like this. This shows positive deviation. So this line will also be here, and this line will be here. Right? So this shows that if I say, supposing I want to find the vapor pressure at this point, right? Where XA is here and XB is this much. What was the expected pressure? The expected pressure was here. But what do I find? The expected pressure is here. So there is what? A positive deviation. Okay. So this shows a graph for positive deviation. And this shows a graph for negative deviation. So sometimes in the exam, you will see a graph, and seeing the graph, you will have to explain. So explain the, the change in the vapor pressure compared to the ideal solution. Explain. So you should explain this is negative deviation. Why? Because AB interactions are more than AA and BB interactions. And in case of positive deviation, what will you write? The vapor pressure is more than the expected vapor pressure, because AA interactions and AB interactions, they are more than AB interactions. Okay, so AB interactions are less. So they reduce the vapor pressure. They increase the vapor pressure. Intermolecular force of attraction is reduced, and so the vapor pressure is increased. Are you able to understand? It is very, very important that you read from the textbook. Then only it will become more clear. Please read. For this topic, I would like to, I will ask your, do you get notes of each topic? After each topic, do you get the notes also? Children?
And we get the video uploaded, ma'am.
Acha, so you only see the video, but you don't see the notes as such. So I will find out if I can send you some brief notes for revision. So if I can, then you can go through those brief notes, and you will be able to understand better. Okay, now there is one more thing that I would like to discuss, one more topic. Let's see whether there is time for that. That is not mentioned in your textbook. Okay, there is. Now, there are some certain solutions of two volatile liquids. They are called azeotropic mixtures. What are azeotropic mixtures? Okay, so to explain an azeotropic mixture, let me tell you that, let me give you an example. Supposing I have a solution of water and ethanol. I have a solution of water and ethyl alcohol. I have 50% water and 50% ethyl alcohol. You know, water is completely soluble, or ethanol is completely soluble in water. So I have a mixture of ethanol and ethyl alcohol, and I want to separate it. How will I separate? Can you tell me? What is the method that I will use to separate? Anyone? Hariharan, you are muted. Please unmute and then answer.
Now to separate water and ethanol. Or
Water and ethanol. How will I separate the two? They are miscible. Vaishnavi?
Ma'am, by process of distillation.
By process of distillation. Sai Kalyan, are you there? I didn't hear you for a long time.
Yes, ma'am, I'm there.
Yeah, so Vaishnavi says that I can separate water and ethanol by distillation, right?
Yes, ma'am.
Do you understand distillation?
Yes, ma'am.
Yeah, so supposing instead of ethanol and water, I had water and mixed with it sodium chloride, salt. I had a salt solution. Then I could use distillation very easily, isn't it? I could use distillation very easily. Why? Because do you recall seeing a distillation apparatus in school?
I don't remember, ma'am, but I just for now I remember that converting water into its vapor state is distillation.
Yeah, so what is distillation? It is a process of evaporation followed by condensation. That is what distillation is, isn't it? So I am not good at drawing, and I didn't expect that I will be explaining this. So I didn't keep a diagram ready. So this is how you do a distillation. This is your distillation flask here, right? Distillation flask. And here you have what? H2O and salt, right? And then you heat it from here, heat. So what will happen when I heat it? Only water, because salt is a non-volatile solute. So what will happen? Water will form vapor when I heat, and then what I do is I take it through a condenser. You remember the name of this condenser? It is known as Liebig's condenser. Okay, so these are general knowledge things which people in chemistry should know. This is a Liebig's condenser, right? So it has two jackets. So here in the outer jacket, there is water continuously flowing in and out, right? It's going out and flowing in continuously. And because of that, the vapor which comes in here, by the time it reaches, it gets condensed. And when it gets condensed, when it reaches here, it changes into water again. So evaporation followed by condensation. So here you collect water, and after some time, what is left behind is salt. Okay. So when salt is separated from water, what is the type of, it was very easy. We separated it by distillation. But now if I have to separate ethanol and water, what will I do? Can I do the separation by distillation here?
it is fractional distillation, ma'am.
I will have to do fractional distillation. What is fractional distillation? In fractional distillation,
Like glass.
yeah, you use a fractionating column, right? So why do we need fractional distillation? Can you tell me? Anyone? Why do we need fractional distillation?
If both of the liquids have a very close boiling point, ma'am.
Yeah, both the liquids are volatile. Both the liquids are volatile. So supposing instead of salt here in distillation, what is the problem? Supposing instead of salt, I had ethyl alcohol, right? I had ethyl alcohol instead of salt. Then if I heat it, what will happen? Well, how much was water? 50%. And how much was ethanol? 50%. When I heat it, some vapor of ethanol and some vapor of water will form, right? So what will be the composition of the vapor? What will be the composition of the vapor? Will it be 50% vapor of ethanol and 50% vapor of water? Will it be like that?
It
No.
will be a mixture.
The mixture here will contain more vapors of ethanol, right? It will contain more vapors of ethanol and less vapors of water. Why? Because ethanol is more volatile than water, right? Ethanol evaporates more than water. More at the same temperature, the vapor pressure of ethanol is higher than vapor pressure of water. So the vapor will contain more vapor of the more volatile component. So what will happen now? That vapor which has more ethanol will rise up here and will get condensed. So when I collect here, I will still have ethanol and water, but now I will have only 40% water and 60% ethanol. Why the percentage of ethanol has increased? Because my vapor was also richer in ethanol. Now what will I have to do? I'll have to take it back and then do distillation again. So when I do it again, what will happen? I will get 30% and then 70% ethanol. So I will have to do repeated distillation till to prevent the repeated distillation, what we do is we do fractional distillation. So in fractional distillation, there is this fractionating column, which looks like this, right? So when the vapors rise, they go through this fractionating column. So when the vapor goes here, because suddenly the volume increases, the vapor condenses. And when it condenses, the more volatile component, it goes up, and the less volatile component falls back. So by the time the vapors reach here, it is richer in ethanol. But there is one more difficulty here. When the composition of ethanol becomes 95%, and there is only 5% water, so 95% ethanol plus 5% water, I cannot separate it further by fractional distillation. Why? Because at this composition, at this composition of ethanol and water, the composition of solution will be same as composition of vapor. Okay, so when I heat it, the vapor will also contain 95% ethanol and 5% water. So beyond this, I cannot separate it by fractional distillation. So such mixtures where composition of the solution is same as the composition of vapor, they are known as azeotropic mixtures. Azeotropic mixtures. So azeotropic mixtures are mixtures of two solutions, of two liquids, where the composition of the vapor is same as the composition of the liquid, and so it cannot be separated by fractional distillation. Do you understand? So by fractional distillation, I can only get 90% ethanol. I cannot get 100% ethanol. Okay, so 90% ethanol, it is, when you learn alcohol, you will know, it is known as rectified spirit, right? And 100% ethanol is known as absolute alcohol. Okay, so you cannot prepare absolute alcohol by fractional distillation. Why? It is because ethanol and water, 95% ethanol and 5% water, they make a azeotropic mixture where the composition of the solution is same as the composition of the vapor. Okay, so if I take 50% ethanol, just the last bit, 50% ethanol plus 50% water, this is the composition of the solution. But what will be the composition of the vapor? The composition of the vapor will be 60% ethanol plus 40% water. Why? Because the vapor will be richer in ethanol because ethanol is more volatile. Did you understand something? Okay, so that is known as azeotropic mixture. Now, last 2 minutes, tell me if you have any doubts.
No doubts.
Good. Sanjay has no doubts. Hari Haran,
No doubts, ma'am.
Sai Kalyan,
No, ma'am, no doubts.
Hari Raghav was quiet today. Tell me, any doubts? Ashwin,
No, ma'am.
Ashwin. Yes, Ashwin, tell me.
No doubts, ma'am.
Vaishnavi,
No doubts, ma'am.
very good. Now, children, there is a test coming up for you from haloalkanes and haloarenes, right? I want all of you to read the textbook properly. I want all of you. When is the test? Do you know the date?
Next week, sir.
Next
I guess
Saturday,
29, right?
ma'am.
29, ma'am.
Okay, okay. So before that, I will find out if possible. I will, if they agree, if the learning room administrator agrees, then I will send you the notes. So then you can read through the notes also. Sometimes you understand better, all question answers and everything is given. So you can try that. Okay. So wish you all the best for the test and now see you next week. So next week we will start with colligative properties. Okay. So see you. Bye.
Thank you, ma'am.
Thanks, ma'am.
Thank you,
Thank
ma'am.
you, ma'am. Bye, ma'am.
Thank you, ma'am.
Bye.